Imagine this. It's Saturday night. You've been invited to the party of the century.
Yeah,
And I don't mean just, casual get-together. I mean the event. Everyone's been talking about it for weeks.
I'm with you.
So you walk up to the house, and you can feel the bass thumping in your chest from, the end of the driveway.
Oh, good sign.
It's a great sign. You step inside, and the setup it's immaculate. The mood lighting is perfect. There's a table that is absolutely groaning under the weight of chips, dip, fancy hors d'oeuvres, everything.
It works.
The fridge is stocked with every drink you can possibly imagine. The playlist is incredible. It's the perfect party.
Sounds like a great night.
It should be. But you look around the living room, it's empty.
Huh.
You check the kitchen, empty. You wander out to the backyard, nobody. You check your phone, you post on social media, hey, I'm here, where's the crew?
Right.
You wait, and you wait. You even check the bathroom just in case everyone is hiding in there for some reason. Nothing. It's just you, the music, the food, and this great silence.
That is a very visceral way to put it.
Well, that is the exact visualization that the Planetary Society uses to describe the topic we are tackling today. We're looking at a universe that has all the ingredients for a massive, loud, raucous party, stars, planets, time, chemistry, and yet we seem to be the only ones eating the chips.
And that unsettling feeling you just described, that knot in your stomach, that is the heart of the Fermi paradox.
The Fermi paradox. Where is everybody? I feel like this is one of those questions that hits you when you're a kid looking up at the sky, and then you kind of forget about it until you're an adult having an existential crisis at 2 a.m.
It definitely fuels some late-night anxiety. But it's not just a philosophical question. It's a genuine scientific anomaly.
Right, and that's why we're doing a deep dive today. We aren't just going to speculate about, little green men. We have a massive stack of research here. Papers by Sandberg, Drexler, and Ord. Analysis from Robin Hanson, transcripts from Brian Cox, Isaac Arthur, Melody Sheep. We are going to try to answer the question of why the universe is so quiet.
And it seems from all that reading that there are really only three ways this can go.
Exactly. When you strip away all the sci-fi fluff, there are three main categories of explanation. 1, they aren't there.
We're alone.
2, they are there, but they're quiet, they're hiding.
Or sleeping.
Or 3, they are there, and it's terrifying.
Empty, hiding, or hostile.
Yeah. And I don't know which one I'm rooting for, honestly. They all seem to have some pretty heavy baggage.
They do. But before we even get to the solutions, I think we have to properly frame the scale of the problem. Because I think when people hear aliens, they think about UFO sightings or conspiracies.
Right. Fuzzy pictures of a weather balloon.
Exactly. They don't think about the math. And the math is where the paradox really lives.
Okay, let's talk numbers. Because the numbers are, frankly, they're ridiculous.
They are. So let's start with just our neighborhood, the Milky Way galaxy. Current estimates put us at somewhere between 100 billion and 400 billion stars.
400 billion. That number is so big it doesn't even mean anything to my brain. It's just a sound.
Okay, do I have to think of it this way? If every star in our galaxy was just a single grain of sand, you could fill an entire Olympic-sized swimming pool with them.
Okay, that helps a little.
And that's just our galaxy. We think there are maybe 2 trillion galaxies in the observable universe.
Yeah.
So that's 2 trillion swimming pools full of sand.
My brain just broke.
And we know now, thanks to telescopes like Kepler, that planets are common. They are not rare. It's probably the rule, not the exception, that a star has planets.
So there are likely billions of Earth-sized planets in the right zone for liquid water just in our galaxy alone.
Billions. The real estate is there. The ingredients are there. But the thing that really messed me up when I was prepping for this, the thing Brian Cox talks about, is the time factor.
The time gap. This is the critical piece, isn't it?
It's everything.
So the universe is about 13.8 billion years old. Our Earth is only 4.5 billion years old. That means there was a lot of time before we even showed up to the party.
Billions and billions of years. And this is the point Brian Cox makes so well. Imagine a civilization that arose just 1 million years before us.
Just 1 million.
In human history, 1 million years is forever. We were barely using stone tools 1 million years ago. But in cosmic time, if the universe is a 24-hour clock, 1 million years is. It's a fraction of a second.
It's a rounding error.
Exactly. But look at what we've done in just a few hundred years. We went from Isaac Newton figuring out gravity to walking on the moon in less than 500 years.
We went from horse carriages to the International Space Station.
Now imagine a civilization with a 1 billion-year head start.
A billion years! I can't even picture what technology looks like after a billion years. It would look like magic to us.
It would be indistinguishable from magic. And more importantly, they would have had time to go everywhere.
Right, this is the expansion part of it.
Even with slow ships that don't break the laws of physics, no warp drive, you can cross the entire galaxy in a few million years. If you reproduce and spread from star to star, you can colonize every single star system in the Milky Way in a geological blink of an eye.
So if there was even one civilization that started a little bit earlier than us,
They should be everywhere.
there should be a Starbucks on the moon, there should be a spaceship parked on the White House lawn.
Precisely. The galaxy should be teeming. It should be like Times Square on New Year's Eve, but instead we look out and we see rocks, gas, silence.
That is the Great Silence. And I believe it was the physicist Enrico Fermi who first shouted this out over lunch.
Legend has it, yes.
Yeah.
It was in the 1950s at Los Alamos. He was having lunch with some other brilliant physicists. They were all talking about space travel and aliens, and he just blurted out, "But where is everybody?"
I love that. Just a casual lunch conversation that breaks our understanding of reality.
And then later, another physicist, Michael H. Hart, he formalized it in 1975. He basically proved that if they existed, they would be here. Since they aren't here, they must not exist.
Well, that seems like a wrap on the episode then. Thanks for listening, everyone.
If only it were that simple.
Right. So let's unpack the first major explanation, the they aren't there theory. And this brings us, of course, to the Drake equation. I feel like you can't do a deep dive on aliens without mentioning Frank Drake.
You really can't. It's the foundational text, so to speak, of this whole field.
But help me out here, because I see this equation everywhere, n equals r star times fp. It looks like a nightmare from algebra class. What is it actually trying to do?
Well, Jill Tarter from SETI gave the best definition I've ever heard. She called it a tool to organize our ignorance.
Organize our ignorance. I like that.
It's not an answer. It's a list of questions.
Yeah.
It just breaks down the massive problem of, are there aliens, into smaller, more manageable pieces.
Okay, so what are the pieces?
Well, you start with the rate of star formation in our galaxy. Then you multiply that by the fraction of those stars that have planets.
Okay, that makes sense.
Then, the number of planets per star that could actually support life, the habitable zone planets. Then you get to the really hard parts.
The biological unknowns.
Exactly. What fraction of those habitable planets actually develop life? That's the variable $5. Then, what fraction of that life becomes intelligent? That's $5. And finally, the big one, how long do they last?
That last one, the L factor. That's the real kicker, right?
It is. L stands for longevity. How long does an intelligent communicating civilization stay detectable? We've only been broadcasting radio signals for about 100 years. If civilizations typically blow themselves up after 200 years.
Then L is very small.
Very small. And the galaxy could be full of ruins, but empty of anyone to talk to, just because everyone dies young.
Okay, but here is where we get to the new stuff. The source material for this deep dive included a paper by Sandberg, Drexler, and Ord titled Dissolving the Fermi Paradox. And honestly, reading the abstract, I felt like they were telling me we've been doing the math wrong for 50 years.
In a way, we have. Or rather, we've been being far too confident in our guesses.
How so?
Think about how people usually use the Drake equation. They make what are called point estimates. They say, okay, let's just guess that 1% of stars have life, and let's guess 1% of those get smart. They plug in specific single numbers.
Right. You plug in your best guesses, you hit the equals button, and you get a number of aliens. And usually it's a big number.
It is. Even with conservative guesses, you often end up with thousands or even millions of civilizations in the galaxy. And that creates the paradox. But the problem is, we have no idea if those numbers are right.
We're just guessing.
We are guessing wildly. And when you multiply a bunch of guesses together, you don't get a good answer. You get a very messy result. Sandberg and his colleagues argue that you shouldn't plug in a single number. You should plug in a probability distribution.
Okay, you're getting into stats territory here. Break that down for me. What is a probability distribution in this context?
Imagine you're baking a cake, but you lost the recipe. You know it needs sugar, but you don't know if it needs a teaspoon of sugar, or a cup of sugar, or an entire dump truck full of sugar.
That's a very risky cake.
Exactly. Now, a point estimate is if you just guess 1 cup and bake the cake. A probability distribution is admitting, I don't know, but the recipe probably calls for something between a teaspoon and 2 cups. You're giving a range of possibilities, not just one number.
Okay, so you're acknowledging your own uncertainty.
Precisely. And for some factors in the Drake equation, like abiogenesis life starting from dead matter, our uncertainty is that wide. It could be super common, or it could be so fantastically rare it only happened once in the entire history of the universe.
We have no other data points. Just Earth.
So instead of saying the chance of life is 1 in 100, we have to admit it might be 1 in 10, or it might be 1 in 10 with 100 zeros after it. We just don't know.
Right.
And here's the magic of the math in that paper. When you replace those single-point guesses with these wide ranges of scientific uncertainty, when you actually account for how much we don't know, the final result changes drastically.
How does it change?
It spreads out. And it turns out there is a huge chunk of the final probability that lands on 0.
Zero other civilizations?
0. The paper concludes that based on our current scientific uncertainty, there is an ex-ante probability. That means, looking at it before we find any new evidence, of between 53% and 99.6% that we are alone in the Milky Way.
Wait, pause. 99.6%.
That's the upper bound of their probability model. Even across the entire observable universe, they calculate a 39% to 85% chance that we're the only conscious observers out there.
That flies in the face of everything I've ever heard. You always hear, the universe is so big, there must be others. It feels intuitive.
That intuition comes from assuming that life is easy to start. If life is hard, if it's really, really, really hard, then the size of the universe doesn't matter. The hard part cancels out the big part.
So dissolving the Fermi paradox basically means there is no paradox. That silence is exactly what we should expect because we are, for all intents and purposes, a statistical freak accident.
It suggests that an empty galaxy is a perfectly consistent outcome of our current knowledge. We shouldn't be surprised by the silence. We should be looking in the mirror and realizing just how weird and improbable we are.
That is, I don't know if that's comforting or terrifying. It makes me feel incredibly lonely.
It brings us right to the rare earth hypothesis. If the math says we might be alone, we have to ask, what makes Earth so special? Did we just win the cosmic lottery?
I read the John G. Kramer article and the notes on Ward and Brownlee's book, and it seems like we didn't just win the lottery once. We won the lottery every single day for 4 billion years straight.
It certainly looks that way. It's not just about being in the Goldilocks zone, the right distance from the sun for liquid water. That's just step one on a very long list.
Okay, so let's list some of these hurdles, because it's not just add water and wait. First, there's the neighborhood.
The galactic habitable zone. You don't want to be in the center of the galaxy.
Why not? The galactic core looks bright and fun in pictures.
It's a death trap. The star density is way too high. You have constant supernovae stars exploding and blasting any nearby planets with sterilizing radiation. You have the supermassive black hole at the center fleeing things around. It's just too chaotic for complex life to evolve over billions of years.
Okay, so you want to stay out of downtown, but you can't move out to the boonies either.
No. If you go too far out to the rim of the galaxy, there aren't enough heavy elements, what astronomers call metals, which is basically anything that isn't hydrogen or helium.
Like iron, magnesium, silicon.
All the stuff you need to build a rocky planet like Earth. The universe was mostly hydrogen and helium at the start. You need generations of stars to live and die and explode to create the heavy stuff. The outer rim of the galaxy is just gas, no rocks. No Earth.
So we are in the galactic suburbs, nice and quiet, good schools, plenty of iron.
A very nice stable orbit. Then there's our star.
The sun.
It's actually a very polite, stable star. It's a yellow dwarf. If it were a lot bigger, it would have burned out in a few million years. Not nearly enough time for evolution to get going. If it were smaller, like a red dwarf.
And red dwarfs are the most common type of star, right? By a lot.
They are, by far. But they are temperamental. They have these massive solar flares that can strip the atmosphere off a nearby planet in an afternoon.
That's not good for business.
Not at all. And to be warm enough for liquid water, a planet has to be really, really close to a red dwarf, which means it gets tidally locked.
Where one side is always facing the star.
Exactly. One side is perpetually cooking in daylight, and the other side is frozen solid in eternal night. It's not a great place for life as we know it.
Okay, so we have the right address in the galaxy, the right kind of star. Now let's talk about the bodyguards. We have Jupiter.
The Jupiter shield. This is a big one. Jupiter is so massive that its gravity completely dominates the outer solar system. It acts like a cosmic vacuum cleaner.
A bouncer for the inner planets.
A very good bouncer. It sucks up or flings away asteroids and comets that would otherwise be heading for us. Without Jupiter, the rate of cataclysmic impacts on Earth would be much, much higher.
So without Jupiter, Earth gets punched in the face by a city-sized rock every few thousand years instead of every few million.
Something like that. And complex life, dinosaurs, mammals, us. We need long periods of stability. We can't handle constant resets from the sky.
Speaking of stability, the moon. I never realized how weird our moon is until this deep dive.
It's a complete freak of nature. For a planet our size to have a moon that large, it's almost unheard of in the solar system.
And it wasn't just captured by our gravity, right? The theory is it was a collision.
The leading theory is the Theia impact. A Mars-sized planet smashed into the proto-Earth billions of years ago. The debris from that cataclysmic collision eventually coalesced to form the moon.
Wow.
But that violence did something crucial. It gave us this huge moon that stabilizes our axial tilt.
This is the thing that gives us our seasons.
Right. Earth tilts at about 23.5 degrees relative to its orbit. That gives us summer and winter. But without the moon acting as this massive gravitational anchor, that tilt would wander chaotically over millions of years.
What would that look like?
We might tilt over to 90 degrees. Imagine the North Pole pointing directly at the sun for 6 months straight. The oceans would literally boil on one side of the planet and freeze solid on the other. It would create climate swings that are completely incompatible with complex life.
Okay, so no moon equals crazy weather equals no civilization.
Almost certainly. And you can keep going down the list. We have plate tectonics, which acts like a thermostat for the planet, recycling carbon and regulating the climate. We have a magnetic field that protects us from solar wind. It's just one lucky break after another.
And that's just the planet. Then you have the biological hurdles, the hard steps.
The Alice paper talks about this. It's the idea that evolution isn't a smooth, predictable ramp upwards. It's a series of giant, improbable cliffs you have to somehow scale.
Okay.
We look at the fossil record on Earth and we see these huge gaps of time where almost nothing happens. For example, life starts pretty quickly after the planet cools down, simple, single-celled stuff, prokaryotes. But then, nothing changes for more than a billion years. A billion years of just slime.
A billion years. That's a quarter of the entire history of the planet.
It's just slime. Until, by some incredible fluke, one cell swallows another cell and doesn't digest it. They become a team. That's the eukaryotic cell, the basis of all complex life, all plants and animals. That seems to have happened exactly once in Earth's history.
One time. A single chance event.
And then you have another long wait to get to multicellularity. Then another wait to get sexual reproduction, then another wait for intelligence. Aldous points out that the time between these hard steps is roughly equal, which mathematically suggests they are all independently unlikely events. They are hard filters.
So this is the filter behind us theory. We are the survivors. We made it through the cosmic obstacle course that killed everyone else.
That is the optimistic view, yes.
Optimistic. Being the only survivor in a galactic graveyard is optimistic.
Compared to the alternative, absolutely. Because the alternative is that the filter isn't behind us. It's ahead of us.
Oh, right. The we are doomed scenario.
If the filter is ahead, it means that getting to where we are now is easy. Slime turns into monkeys. Monkeys turn into podcast hosts. That happens all the time, all over the galaxy. But the next step, going from a planetary civilization to a stable star-faring one, that's the impossible part.
So the reason the universe is empty is because as soon as you get smart enough to build a radio, you also get smart enough to build a nuke.
Or a designer plague. Or runaway artificial intelligence. This is where the L factor from the Drake equation comes back to bite us. Maybe civilizations are naturally transient, they flicker into existence, and then snuff themselves out.
The sources mentioned asymptotic burnout, which sounds less like a violent explosion and more like just giving up.
It's the ennui filter. Isaac Arthur discusses this. Imagine a civilization solves all its material problems. Unlimited clean energy, perfect healthcare, total abundance, maybe even a perfect virtual reality. Do they still have the drive to build giant, slow colony ships and spend thousands of years floating in the dark void just to terraform a dead rock?
When they could just stay home in a perfect virtual reality paradise? Probably not.
Exactly. Maybe they just turn inward. They upload their brains into a server, simulate a perfect universe, and turn off the external lights.
No.
They don't expand. They estivate or just stop caring about the physical world. They become quiet.
So we are either special and lucky because the filter is behind us, or we are completely average and walking straight off a cliff that everyone else has already fallen off of.
That is the dichotomy. And this is why the philosopher Nick Bostrom says, No news is good news when it comes to the search for extraterrestrial life.
How so?
He argues that if we found life on Mars, even just simple fossilized bacteria, it would be the worst news in human history.
Wait, really? I feel like finding life on Mars would be the coolest, most celebrated discovery ever.
It would be cool scientifically, but existentially it would be a nightmare. Because if life started independently twice just in our own solar system, that means the first hard step of biogenesis is not hard at all. It means life is easy. It means the universe is absolutely teeming with slime.
And if the universe is teeming with life but nobody is answering the phone?
Then the great filter, the thing that kills civilizations, must be ahead of us. It means the cliff is real and we're walking towards it. We want life to be rare. We want to be the only slime that got lucky. Because if we aren't special, we are probably dead.
Wow. Okay, I'm going to need a second to process that. Please let Mars be a dead, sterile rock. That's a new bumper sticker.
It's profoundly counterintuitive, but yeah.
All right, let's pivot. Let's assume, for the sake of argument, that we aren't alone. Let's assume some civilizations survived their filter. This brings us to part 3, the loud aliens. Because if they are out there and they are advanced, shouldn't we see some evidence?
This brings us to the concept of grabby aliens.
Grabby. I love the terminology in this field. This is Robin Hansen's term.
Yes, Hansen creates this really useful distinction between quiet aliens who stay home, die out, or turn inward, and grabby aliens who expand aggressively and visibly change the universe around them.
And the logic here is based on the unstoppable power of exponential growth.
Which brings us back to the von Neumann probe idea.
Right, let's really break this down so it's crystal clear. A von Neumann probe is a self-replicating spacecraft.
Imagine you build a robot, you send it to a nearby asteroid. It has mining equipment and, let's say, a sophisticated 3D printer. It lands, it digs up some iron and nickel and carbon, and it builds a perfect copy of itself.
So now you have 2.
Then they both fly to new asteroids. Now you have 4. Then you go to new asteroids, you have 8. Then 16, 32. It's a virus, a mechanical virus spreading through the solar system and then the galaxy.
And exponential growth is no joke. I remember the story about putting rice on a chessboard. 1 grain on the first square, 2 on the second, 4 on the third. It starts small, but halfway through the board you have more rice than exists in the entire world.
Exactly. Even if these ships are really slow, let's say they travel at just 1% the speed of light, which is achievable with known physics like fusion rockets, they could saturate the entire Milky Way galaxy in something like 10 to 100 million years.
Which, again, is nothing in cosmic time.
It's a blink. So if one civilization at any point in the last 13 billion years decided to do this, the galaxy would be full of probes. Every star system would have one.
So where are they?
That's the problem. Hansen runs these detailed simulations. Imagine the universe is a big, empty canvas. Life pops up randomly in different spots, little dots. If a civilization is grabby, it starts expanding in a sphere, like a bubble growing on the canvas.
Okay, expanding bubbles of civilization?
Eventually, these bubbles would meet and merge. They would fill the whole canvas. If grabby aliens were common, or if even one of them started really early, Earth would have been inside someone's bubble billions of years ago.
We would have been colonized before we're even monkeys. Our planet would just be part of their galactic empire.
Precisely. The fact that we are sitting here on a pristine planet looking at an apparently empty sky implies that we are not inside a bubble, which means either grabby aliens are impossibly rare or we are just incredibly early to the party. We might be one of the very first bubbles to start forming.
But I still hear people say, oh, space is just too big. Maybe they are out there, but they just can't get here. The distance argument. It feels like a simple answer.
It appealed to our intuition because we're used to cars and planes. But physics actually offers a loophole. Brian Cox talks about this. It's Einstein's special relativity.
Time dilation. The faster you go, the slower time passes for you.
Yes. We think about travel time from the perspective of the people staying home on Earth. We say it takes 2.5 million years to get to the Andromeda Galaxy. And that is true for the observer on Earth. If you get on that ship, I won't see you arrive for 2.5 million years.
But for the person on the ship,
if you can build an engine that constantly accelerates you closer and closer to the speed of light, say 99.999% time slows down for you dramatically, the distance effectively shrinks from your point of view. You could fly to Andromeda, a journey of millions of light years, in what feels like maybe 40 or 50 years to you. A single human lifetime.
So you could actually conquer the galaxy in a single lifetime.
From your perspective, yes. You just can't ever go home again because everyone you knew would be dead for millions of years. But the point is, physics does not prevent galactic colonization. Energy and engineering are the limits, not the fundamental laws of the universe.
So it's too far is just a bad excuse. If they wanted to be here, they could be here.
They could. And since they aren't, and we don't see any of their techno-signatures,
Technosignatures, like a Dyson sphere. That's the classic one.
a Dyson sphere or Dyson swarm is the ultimate loud sign. A civilization gets so advanced, it needs all the energy from its star, so it builds a megastructure of solar panels to surround it.
What would that look like to us?
Well, the star would disappear in visible light, but all that energy has to go somewhere, so it would glow like a furnace in infrared heat.
Hmm.
We have telescopes scanning the sky for exactly that signature, a star that's weirdly bright in infrared, but dark in visible light.
And we haven't found any.
We've looked at millions of galaxies. We haven't found a single definitive Dyson sphere. The universe looks remarkably natural. No galactic-scale construction zones, no star lifting where they're mining stars for fuel, no evidence of industrial pollution in the atmospheres of exoplanets, just wilderness.
Okay, so the they aren't there argument is looking pretty strong, but now we have to turn to the third lens, the one that keeps me up at night, the one that says, they're there and they're watching us right now and they have a finger on the trigger.
The dark forest theory.
This comes from Cixin Liu's science fiction novel, The Three-Body Problem. And honestly, it's one of the most terrifying concepts I've ever encountered because it makes so much cold, logical sense.
It's applied game theory to the Fermi paradox.
Let's role-play this for a second so the listeners really get the horror of it. Imagine the universe is a dark forest at night. It's pitch black, you are a hunter, you have a gun, you are creeping through the trees.
Okay. And I'm trying to be as quiet as possible because I know there are other hunters out there.
Right. And you don't know if the other hunters are nice people looking for friends or if they're psychopaths. You just know they are armed and dangerous. Now, suddenly, you sip on a twig, snap, or you light a small fire to keep warm.
I reveal my position.
You reveal your position, and I, another hunter, see your fire from across the valley. I see you. Now I have a choice. I can walk over and shout, "Hello, friend or foe?"
Or you can just shoot me.
Right. What's the rational move?
Well, if I assume you're rational, you have to shoot me.
Whoa, that's harsh. I might be friendly. I might have chips and dip from the party at the beginning of the episode.
You might, but I can't know that for sure. And more importantly, I can't know if you know that I am friendly. This is what the book calls the chain of suspicion. Even if we are both fundamentally nice, we can't trust that the other knows that.
And the stakes are total annihilation.
Exactly. If I take the risk and guess wrong, if I assume you're nice and you shoot me, I die. My entire civilization dies. But if I shoot you first, I guarantee my own survival. The only safe move, the only truly rational move in the universe of unknowns, is to destroy any other civilization the moment you detect them.
Shoot first, ask questions never.
And there's another layer to this that makes it even worse. The technological explosion.
Right. You might look at us Earth humans right now and say, oh, they're cute. They just figured out radio. They aren't a threat to my ancient, powerful empire.
But look at our timeline again. In 100 years, we went from muskets to thermonuclear weapons. In cosmic time, that's an instantaneous leap. So if I'm an old civilization and I see you, a primitive one, I can't just leave you alone, because in a cosmic blink of an eye, you will be an advanced civilization that could be a threat to me.
So a peaceful baby civilization is just a future threat waiting to happen.
Exactly. So the brutal logic of the dark forest dictates wipe them out while it's still easy and cheap to do so.
God, that is bleak. And the weapon we'd use. We aren't talking about invading with soldiers, right? We aren't talking about Independence Day where a giant mothership hovers over New York.
No, that's inefficient and risky. If you want to kill a civilization in the dark forest, you use a relativistic kill vehicle.
An RKV.
It's terrifyingly simple physics. It's just Newton's second law. Force equals mass times acceleration. You take an object, it doesn't have to be big, maybe the size of a car, maybe just a refrigerator.
Yeah.
Put a powerful engine on it, and you accelerate it to, say, 95% the speed of light.
Okay, so it's a really fast rock.
At that speed, the kinetic energy is astronomical. A small object hitting Earth at near light speed would impact with the force of all the nuclear weapons on the planet going off at once. It would spiralize the entire surface.
And you would never see it coming.
That's the truly scary part. Since it's moving almost as fast as light, the light reflecting off the ship only arrives a fraction of a second before the ship itself. You'd be looking at the sky, everything is fine, and then lights out. No warning, no negotiation. Game over.
So if the dark forest theory is real, the reason the universe is silent is because everyone who was loud
is dead.
And here we are, Earth, blasting I Love Lucy and Taylor Swift into the cosmos, sending out the Voyager probes with literal maps to our house.
We are essentially walking through the dark forest, screaming at the top of our lungs, I'm over here, I'm delicious, and I don't have a gun.
We are the noisy toddler at the party.
It explains the Fermi paradox perfectly. The universe isn't empty, it's just holding its breath. The only civilizations left are the ones who learned how to hide.
This also connects to the berserker idea, right? Which is somehow even
The
worse.
berserker hypothesis, yeah. This is the idea that maybe it's not other living civilizations hunting us. Maybe it's an automated system left over from an ancient war.
Killer robot.
Ancient killer robots. Imagine a civilization millions of years ago fought a terrible war. They built self-replicating machines. Von Neumann probes programmed to destroy any emerging technological signature. That civilization died out, but the machines are still out there, patrolling, waiting.
Like a cosmic minefield that nobody remembers laying.
Exactly. As soon as a civilization gets smart enough to turn on a powerful radio or build a starship, the berserkers activate and reset the clock. The Great Silence is a graveyard maintained by automated groundskeepers.
Okay, I'm officially terrified. Can we please move to the exotic solutions? Please tell me there's a theory where I don't get hit by a space rock at the speed of light.
There are. Let's talk about something much stranger but less violent. Let's talk about the estivation hypothesis.
Estivation, that's like hibernation, but for summer, right? Some animals do it to avoid the heat.
Exactly. And this might apply to super advanced civilizations too. Isaac Arthur brings this up. Think about computers. When do computers run most efficiently?
When they're cool. That's why server farms have these massive air conditioning units. Heat is waste.
Precisely. It comes down to thermodynamics. There's something called land hours limit. It basically states that it takes a minimum amount of energy to erase a bit of information. And that energy cost goes down as the temperature drops. The colder it is, the more efficient your brain or your civilization scale mega computer can be.
Okay, so what does that have to do with aliens?
Well, the universe right now is actually very hot. The cosmic microwave background, the leftover heat from the Big Bang, keeps deep space at a temperature of about 3 Kelvin. That's incredibly cold to us. But for a super advanced digital intelligence, that's sweltering. It's wasted energy.
So they are waiting for winter.
A cosmic winter. The universe is constantly expanding and cooling. In a few trillion years, it'll be much, much colder, approaching absolute zero. If you are a digital civilization that values computation above all else, you could get trillions of times more processing power out of the same amount of energy just by waiting.
So they are sleeping.
They are estivating. They've powered down, set the cosmic alarm for 10 trillion years from now, and are just waiting. We are here during the hot, messy, inefficient dawn of the universe. They are waiting for the long, cool night to get their real work done.
That makes us sound like the morning people of the galaxy. We're up at 5 a.m. making coffee and all this noise, and the elder gods are just trying to sleep in.
It's a distinct possibility. It explains why they don't talk to us. We are like insects buzzing around in the heat of the day. They're not hostile, they're just not interested yet.
I like that one. It makes me feel less like prey and more just annoying. What about the idea that we are looking for the wrong kind of life entirely?
The life as we don't know it argument. We are, as they say, carbon chauvinists. We assume life needs liquid water and is made of carbon-based molecules.
Melody Sheep's documentary was great on this. They talked about silicon-based life.
Right. Silicon is chemically similar to carbon in some ways. It can form long chains. But it works better in extreme environments. Imagine life evolving on Titan, Saturn's moon. It has rivers and lakes, but they're not made of water. They're made of liquid methane and ethane at minus 180 degrees Celsius. Extremely. But you could, theoretically, have silicon-based life there, or you could go the other way. What about plasma life?
This blew my mind.
It's highly theoretical, but under high-energy conditions in the vacuum of deep space, interstellar dust and plasma can organize themselves into helix structures like DNA. They can replicate. They can pass on information. They could evolve.
So you could have a living nebula, a cloud of dust and gas that thinks.
Potentially. And if that's what most advanced aliens look like, they wouldn't build starships or radios. They would just be, we wouldn't even recognize them as life. We'd look right through them with our telescopes and just see a pretty cloud.
And then there's the one that feels the most relevant to our own solar system right now.
Wow.
The ice worlds hypothesis.
This is a very strong contender for the they are there, but we can't see them category. We tend to look for other Earth's blue marbles with oceans on the surface. But in our own solar system, the most common habitat for liquid water isn't on the surface. It's underground.
You're talking about moons like Europa at Jupiter or Enceladus at Saturn.
Exactly. Enceladus is a tiny moon of Saturn. It's covered in a shell of ice that's miles thick. But underneath that ice, a global ocean of warm, salty liquid water. We've seen geysers shooting out of its south pole. It has all the ingredients for life.
So imagine a civilization evolving down there in that ocean.
Picture what that's like. It's pitch black. You live in a 3D environment just floating. Your sky is a solid ceiling of ice, miles above you. You rely on geothermal vents at the bottom of the ocean for energy and heat, not the sun.
Do they even know there's a universe outside the ocean?
How could they? They can't see the stars. To them, the universe is just the ocean and the ice ceiling. That's it.
They would never develop astronomy.
And they would almost certainly never develop space travel. Think about it. To build a rocket, you need fire. You need metallurgy. You can't smelt ore underwater. You can't start a controlled fire in an ocean.
So they could be incredibly smart, philosophers, poets, mathematicians, but they are trapped.
They are locked in a sealed aquarium for eternity. And since these subsurface oceans seem to be way more common in the galaxy than Earth-like planets with surface oceans, maybe most life in the universe is trapped in the dark, unable to ever signal its existence.
That is so tragic. Billions of civilizations, all alone in their own little boxes, all wondering if they're the only ones.
It's a very quiet tragedy.
Okay, we have covered a massive amount of ground. We've looked at the numbers, with Sandberg's math telling us we might just be alone. We've looked at the filters, all the lucky breaks Earth got. We've looked at the horrors of the dark forest, and the strange, exotic solutions like sleeping AIs and life in frozen oceans.
There's a lot to process.
So let's try to bring this home. What does this all mean for the person listening right now? Because we started with that empty party, and now we have a dozen different reasons why the party might be empty. But how should that make us feel?
I think we should return to Brian Cox's sentiment, which I find to be the most profound takeaway from all of this. He talks about Earth being an island of meaning.
I love this concept. Break it down for us.
Look at the universe purely physically.
Yeah.
It's vast. It's violent. Stars are just burning hydrogen and fusion reactions. Black holes are just crushing matter with gravity. It's grand and majestic, but it's meaningless. A rock doesn't care that it exists. A star doesn't know that it's burning.
Meaning requires a mind. It requires a conscious observer.
Exactly. Meaning is a local phenomenon. It exists only where consciousness exists. And if we are the only intelligent life in the Milky Way, then we are the only island of meaning in a sea of 400 billion dead, thoughtless stars.
That puts a lot of weight on our shoulders.
It changes the entire narrative. It's not about why won't the aliens talk to us. It's about we have a cosmic job to do. We are the candle in the darkness. If we snuff ourselves out, if we let the great filter get us, if we blow ourselves up in a war or ruin our planet, we aren't just ending the human story. We might be eliminating the only meaning that exists in this entire galaxy.
You know, we would be making the galaxy go dark again, in a metaphorical sense.
And that is a terrifying and profound responsibility. It means our survival matters on a cosmic scale. It means we have to get our act together. We have to expand. We have to become the grabby aliens, hopefully in a nice way. We have to spread life and consciousness to the dead stars because nobody else is going to do it for us.
It reminds me of that Arthur C. Clarke quote we mentioned at the start. Two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying.
It's absolutely true. If we aren't alone, we have to worry about the dark forest. If we are all alone, we have to worry about not dropping the torch of consciousness.
But I want to leave our listeners with one final provocative thought. We talked about the great filter and how maybe, just maybe, we are the first ones to pass through it.
The firstborn hypothesis.
Yeah. Think about every science fiction movie we've ever seen. We always look up at the stars and we imagine ancient elders, right? We imagine these wise, ancient civilizations that are millions of years older than us. The Vulcans, the Jedi, the precursors who left giant monuments behind.
We want a galactic parent figure. We want someone to tell us it's all going to be okay.
But what if we are the ancient elders? The universe is 13.8 billion years old, but it will last for trillions of years more. We are living in the cosmic dawn. Maybe the reason we don't hear anyone is because the party hasn't actually started yet. We're just the first guests to arrive.
And we are currently setting up the snacks and putting on the music.
Exactly. We are the ones who will build the monoliths. We are the ones who will leave the artifacts on distant planets for others to find. In a billion years, maybe some new amphibious civilization will crawl out of its ocean, look up at the stars, find the ruins of our achievements, and say, Those are the giants. Those were the first ones.
We are the ancients. That is a powerful place to end.
It really shifts the perspective, doesn't it? So next time you look up at the night sky and feel small, just remember, you might be part of the most important thing happening in the entire galaxy. Thanks for diving deep with us today.
Keep looking up.